Hello, in this short video we're gonna see that compactness implies completeness for a metric space. So let's start with compactness. So I guess you know the usual notion for compactness. We will deal with an equivalent notion, namely sequential compactness. So a metric space X is called sequentially compact if every sequence in X has a convergent subsequence with limit in X. Okay, so this you might also already know from real analysis, and well, this is also true for metric spaces. Okay, now let's prove the following lemma, namely that let's take a metric space and the claim is well, let X be a metric space and it should be compact. So we could also say a compact metric space. And the claim is that X is complete. So what do I mean by complete? Complete means every Cauchy sequence converges as usual. Okay, so for the proof, how do we go about it? Well, we have to start with a Cauchy sequence. So let's start with this. And we want to show that it converges. Okay, so, and the limit should also be in X. Okay, so the idea is very simple. We have the subsequence which converges and has limit in X. And since the sequence is Cauchy, we will show that also the whole sequence converges to X. So let's start simple. So let's just write down the definition. So then there exists, let's say, n1, such that for all n and m, at least n1, we have xn, so, well, for all epsilon greater than 0, xn minus xm are less than, let's say, epsilon over 2. Okay, so now, so we want to fix now our epsilon greater than 0, and we want to prove that the sequence converges. Okay, so now we've used the definition of the Cauchy sequence. We also know that the space is compact, so it's also sequentially compact. So let's use this. So because X is compact, there exists a subsequence, let's call it Xn, nk. So nk is a subsequence of the non-negative integers, and let's say also k non-negative, and that subsequence converges to a point in X. Okay, so that's the definition. Let's unpack once more. So this means, so just unpack the definition of convergence. So there exists an N2 such that for all, let's say, now let's work with the n k's. So for all nk, well, we could also work with k's, doesn't really make much of a difference, but let's work with the nk's. So if nk is at least n2, then we get that x nk minus x is less than, let's say, epsilon over 2. Okay, and now we put the two things together. So we pick our n1 and n2, and now let's say for n equal maximum of n1, n2, and n at least n. So we also have to use the convergence subsequence. So let's say we choose x nk with nk nk at least n, and then we use the usual triangle inequality. So x minus xn. Now this is at most x minus xnk plus xnk minus xn. Okay, so now this, let's do it step by step. So this thing here is at most epsilon over 2 due to convergence of the subsequence. So this is by convergence. And this thing here is also less than epsilon over 2, and this is due to the sequence being a Cauchy sequence. And hence we can conclude that this is less than epsilon, and therefore the sequence xn, where n is at least 0, converges to x, and hence x is complete. Okay, so thanks for your attention, and I hope that at some later video I can use this for some results on local fields, and then to do some stuff with local fields. All right, have a good day. Bye.